operator are this, and for the Hamiltonian H as well. Alright, now it's not quite as simple as that. Okay, so the spherical harmonics are going to come into this eigenfunction here, the U, somehow, because of this link, because of this. So let's, you might find this a bit fuzzed over a little, but let's assume that, let's see, we're bringing in the angular momentum to some extent. It came in with this here, but we're simplifying it by, well, be the next square. But anyway, so let's assume that the eigenfunction now depends on 3 parameters. Before, what was it, chapter 2, way back, we solved only a simplified version of where the wave function was depending only on R, on the position. So now we've got just three parameters: the position and the 2 polar angles, theta and phi. Now let's assume that wave function, eigenfunction here, right? Let's assume that it can be factored, can be split into 2 parts. We did something like this earlier as well. So let's assume there's a spatial part, a spatial function, so big R, that depends on little r is the position. And for the polar angle part, the angular part, if you like, will be the spherical harmonics. Now, that sounds plausible, because if you think about it, the eigenfunctions of these 2 operators, now these 2 operators, they depend on the angles. There's no mention of R in either of these. So if you plug this thing into the eigenequations of L squared or LZ, the R is just effectively a constant, right? As far as these 2 operators are concerned. So you can just cross out the R, both sides of the eigenequation for these 2 operators, right? So this then is an eigenfunction for L squared and LZ, because the R is effectively, as far as its influence on theta and phi, no influence, independent, right? So that's an eigenfunction for the polar coordinates. Now a similar logic, is it true? I'm just wondering the other way around. So the operator's on R. So this will become, well, I'm jumping ahead a little bit, but think about it. So the L squared acts on this U. Now if this U's of this form, right, is the eigenfunction. So the L squared acts on this and will give you an eigenvalue of L into L plus 1. Right? So effectively, they're just numbers, they're constants. Okay? So this here just becomes effectively a constant. Here we'll put L into L plus 1. And if you've got that as a constant, effectively, scalar in effect, this is a scalar, so this then becomes, the whole thing then becomes an eigen equation with R, just R. And since pi and theta irrelevant to R, the eigenfunction for the energy equation becomes really just a function of little r, and this effectively is constant. So that's another way of looking at it. All right. So let's this L hat squared of U. Let's change that to L. In here, replace it with the eigenvalues L times L plus 1, and watch what happens. Okay, so now here's your eigenequation for the angular momentum of L squared. So it's so here's your eigenvalue. So it's h bar squared L into L plus, little l into L plus 1. Right? Where L's just integers. This is revision from angular momentum theory from previous chapter. Okay? So we can rewrite the Schrödinger equation on this side in this form. Okay? So here's your u. Your u we factored into a spatial term r and a polar angle term y. Okay? ry and ry. Now now before we had L hat squared times u, but the u is now ry. Well, I brought the r to the left here, and so we got an L squared ym. Well, that's the left-hand side of an eigenequation for angular momentum. And so the right-hand side becomes then the eigenvalue. Well, that's just h bar squared L plus 1. It's that. So you can replace this by this. So plug it in here, right? And the u, again, ry, and the u, ry, right? Now we have a y in common all through, divide all through both sides by this spherical harmonic, because it's in common, all sides. And you're left with this thing that looks to be an equation entirely in terms of r, right, the position. So that's simplified a lot, right, from that messy, the previous session, that messy Schrödinger equation using the spherical polar coordinates form of the del squared operator with its r and its theta and its phi. It's quite complicated. Well, now we've got something quite a bit easier, and it's all in terms of r. Right? There's no mention of theta and phi anymore. That sort of disappeared with this trick of using the L hat squared operator with its eigenvalue here. Because these are just numbers now, they're scalars, so it's potential. I mean, this is an operator, right? The e's, that's a scalar, that'll be an eigenvalue, right? So you can effectively, these are numbers now. Oh, wait a minute, got an r here. R squared, okay, forget what I just said. But that you can take over. Alright. Now, this here is probably familiar to you as well. The h bar squared L into L plus 1. That's the expectation value of this operator. Okay? But you've also got this effectively mass r squared underneath. So rewrite this term as the expectation value divided by 2 mu r squared. Okay? And that'll just be a number. Now, as a bit of a comment here, again, a reference to classical mechanics. Again, if you don't know what this is, if you haven't studied classical mechanics in detail, this will probably be meaningless. But if you have, this term here is similar, related, equivalent, the quantum mechanical equivalent of the classical mechanical centrifugal potential barrier, which is of this form. Right? Now this L here is now just the classical angular momentum, and this term, this concept pops up when you're analysing planetary orbits. Now, like I say, just a comment, like a footnote, if you like. Damn, I hope it shocked me. That's the neighbour drilling. I hope it doesn't keep up all... damn. So I'm going to have to speak between the drill noises. Alright. Okay, now some more comments. Have a look at this equation here. Well, with this substituted for this. You will see that this r here, that's your eigenfunction. So here's your eigenequation. You can see just by inspection that this big R here, this eigenfunction, will obviously be a function of R and L. It'll, the result here will depend on L. Okay, but there's no mention of M. There's no mention of the component of the angular momentum or the eigenvalue of LZ operator, LZ. There's no mention of M here. Right? It's just this R is going to depend on two things. It'll be some formula with R's in it and L's. R and L. Okay, so that's worth remembering. Now that's you can deduce that just from looking at it by inspection mathematically, but you can also, that makes sense physically as well. Why? Well, because why is that? Because you've got a spherical symmetry. Why is that? Why do we have spherical symmetry? Because we're talking about this, and this doesn't, the angle here doesn't, the polar angles of this number don't come into it. It's just effectively a scalar now, right? So it's really, everything's just a function then of just R. So if that's the case, you've got a spherical symmetry type situation, in which case the orientation of the z-axis, when you've got a system that's spherically symmetric, it's sort of irrelevant, right? It's with spherical symmetry. Okay, so what does it mean to talk about the z-axis in a spherically symmetric system? It's sort of pointless. So it's not surprising this equation here is independent of M. It'll depend only on R and L. Okay, so I'll stop there, and no more drilling, hopefully.